Welcome to this lecture on parametric equations. We had briefly touched upon them a few chapters ago when we did the unit circle and just used them for that. This time around, they're going to do something else for us. On a graphing calculator, it's a little bit inconvenient to graph an ellipse or a circle or a parabola. And that's where parametric equations come in, and they're kind of nice to handle. Here, just a little introduction. Usually we graph the y-coordinate as the function of x. And so where we graph the function f, then we determine the intercepts and other points on the curve and do all kinds of things. However, sometimes both the y-coordinate as well as the x-coordinate are functions of yet another parameter, which may be called t, and sometimes that comes in for time. And in this one here, we come up with two equations. X is a function of t, and y is a function of g, for example. And these are called parametric equations, and they're graphed simultaneously. We still come up with just 1 point for each of these t here. We come up with one x, y coordinate. Our graphing calculator can handle that easily, so we're just going to do that. The first one is going to be 3 cosine t minus 2 for the x and 3 sine t plus 3 for the y. Just a little thing how it's going to look like. We notice for the unit circle, if we use cosine t and sine t, we come up with a circle. Here, the 3 in the front here means the radius, and this 3 here means that it's being shifted up, and this minus 2 here means that it's shifted to the left. So let's see what's going to happen when we graph this. Here's our regular y editor, but that's not the one we can use, so let's get out of it and go to mode, and we go down a few, and right here it says function. That's how we usually graph, and then here it says parametric, and the next one actually says polar coordinate. We're going to stay on parametric equations, so that's what we're going to have. Let's see if we're going to operate in degrees or radians. Let's just do radians. Then we don't have to use large numbers. So let's go over to, quit out of here and go over to the y editor, which now looks quite different. Well, this is where we're supposed to plug in our equations for x and y. So it's going to be 3 cosine of t, and notice when I hit this button here, automatically it gives me a t, indicating that we're in parametric equations. Minus 2, and then the other one is 3 sine t plus 3. Okay, and I'm going to go to the window. That looks quite different, so we're going to graph t from 0 to 2 pi in increments, I believe. I wonder what that is, pi over 12. That looks, I'm not sure exactly, pi over 24 maybe. Let's see. I'm going to do that on the side, and I'm just going to see what that is there. Pi over 12. Oh, that's pi over 24, so in increments of 15 degrees is how we're graphing. X minimum, X maximum, well, we have to change that. It's going to be shifted 2 to the left with a radius of 3, so I may want to go from -6 to perhaps +6. And then, well, actually, let's do it this way, -8 to 8. And for the y minimum, it's going to be shifted 3 up. So I may want to go, and then with radius of 3, I may want to also go to -8 and 8, something like that. There we go, and then we graph. And I don't know what I did, what kind of mistake I made. Oh, I see what I did. There's the -8, there's the 8, and the scale. That really doesn't matter to me. And -8 and 8. Okay, now it should work. Yeah. All right. There we go. Nice circle. Nope, it's not, because it used the standard, so the standard graph or axis. So I'm going to go to zoom and I'm going to say z square, because that will adjust the axis to scale. And now we have a nice circle. And just like I had said, it's centered at -2 and +3 with a radius of 3. Okay, I'm going to copy that and go back to the lecture. So there we go. I'm going to move this all the way up here. So as predicted, circle with radius 3 and centered at the point -2 and 3. -2 and +3. Okay, the next one here. Oh, wait a moment, I did forget something. I did graph the original equations, but actually what we're supposed to do is eliminate the parameter. I quite overlooked that. How can I eliminate the parameter from this one here? I have a cosine t here, I have a sine t here. I can throw them into each other. I can say, okay, I solved this one for t and then put it in there, but that looks really ugly, cosine of an inverse sine. So I'm going to try something else. First, I'm going to take both equations. Sorry about almost forgetting about that, the important thing here that I actually meant to teach. I got so wrapped up into graphing. First of all, what I'm going to do is I'm going to add 2 to both sides for the x, and for the y, I'm going to subtract the 3. Okay. Now what I'm going to do is I square both sides. Actually kind of square everything. So what we're going to come up with is this. Parentheses, square. Whoops. While I'm at it. And the right-hand side is being squared. So cosine squared, sine squared, and of course that's going to be 9, and that's going to be 9. Okay, notice what happens on the right-hand side. Add left sides. Whoops. Add left sides and add right sides. And what happens on the right-hand side when we do that, cosine squared plus sine squared is of course 1 times the 9 that's in front, and that's how we got rid of the sine t, or the t in particular. And of course we add the left-hand side, so it's going to be x squared plus x plus 2 squared plus y minus 3 squared equals 9. And that way we eliminate the parameter t, and here this is the regular equation for a circle. It's just very unwieldy to graph, and that's why I focus right away on graphing these parametric equations. Besides, they're kind of fun. I said I almost overlooked what I meant to do in this lecture. All right, so let's look at the next example. This time we go ahead and do that first, eliminate the parameter t, and we're going to do it in the same kind of fashion. So we're going to subtract 2 on the other side, and we add 3 on this side. Then we're going to square everything. Then unfortunately will take me a while. So I'm going to have this one here, and this one here will be a 9. And I'm going to have this one here, and this one will be a 4 sine squared. Okay. Then, of course, at this point, I cannot add on the right-hand side, because I would add 9 cosine squared plus 4 sine squared, which is not a Pythagorean theorem. So what I'm going to do is I divide first by 9, the first one. So this one is going to be divide by 9. Get rid of it here. And this one divide by 4. Get rid of it there. And now I can add all sides, and I will come up with, on the right-hand side, of course, equals 1 cosine squared plus sine squared, and on the left-hand side, looks a little bit more interesting, plus this here. And because of these unequal denominators of 9 and 4, which are actually 3 squared and 2 squared, this is not going to be a circle, it will be an ellipse. As I said, this is really going to be strange to graph right here, but that's what we're supposed to do, eliminate the parameter t. So what we do instead is, of course, regraph the original parametric equations. Here again, cosine, sine would give us a circle. However, they have different numbers in front of them, 3 and 2, and these are mean that this one is the long axis of the ellipse, so kind of the longer radius of 3, and this one is a shorter radius of 2, and this, of course, is the center that the ellipse is shifted 2 to the right and 3 down, and that's what we should come up with. So let's graph. Okay, that's the one from before. I think I can just go in there and switch a few numbers. 3 cosine t plus 2 in this case. 2 sine t minus 3. And then I just hit the graph button. And there indeed it is. The axes are actually to scale, so this truly is an ellipse. I guess I could zoom in a little bit, and I will do that. So zoom in here. That's pretty close to the center of the ellipse. And there it is. Whoa, now it almost looks too big. I just leave it at this here, or I zoom out again. Yeah, I think I zoom out again. Right there, right there. Yeah, that's good enough. Take a screenshot, plug that into our lecture. Okay. And here, let's see what I had said before. As predicted, an ellipse with long axis 3 and short axis 2, and centered at what was that here? Positive 2 and negative 3, right? Positive 2 and negative 3. With that, I'll stop this lecture here and we'll continue a little while later. Welcome back to this lecture on parametric equations, and this is the next one. Same kind of deal. We have x to secant t plus 3. We have y equals 4 tangent t plus 2. We're supposed to eliminate the parameter t, and then graph the original equations. A little bit different though. Notice that instead of cosine sine, we have secant tangent. Remember, for the cosine sine, what we did is we squared it at some point and then used the Pythagorean. Let's just see if the same method could work for the secant and the tangent. In fact, there is a Pythagorean which says 1 plus tangent squared equals secant squared. So let's see how we can do that. We're going to take the two equations and we proceed just like we did before. We subtract 3 on both sides on the first one, and we subtract 2 on both sides for the second one, and then we square both sides, and of course that's going to be the lengthy part. I don't think I could have shortened that in any case anyway, unless I would have unless I would have typed everything ahead of time. So square the left-hand sides, square the right-hand sides where we will have a 4 here and a 16 here, and secant squared and tangent squared. And then we divide both sides by 16. So we'll do that. The first one we'll divide by 4, and the second one we divide by 16, and then we add the two sides, and no, we don't. Why not? Because the Pythagorean does not say secant squared plus tangent squared. What it says instead is secant squared minus tangent squared equals 1. So in this case, we subtract both sides. So subtract both sides, and then with the Pythagorean, what we have on the right-hand side will be a 1. I think I'm going to take this away here. Don't need it. So secant squared minus tangent squared equals 1 on the right-hand side, and on the left-hand side it's going to be x minus 3 squared over 4. And as I said, we subtract. So minus y minus 2 squared over 16. Well, the 4 here, which is 2 squared, and the 16 here, which is 4 squared, they have some meaning. The 3 and the 2 here probably again means that it's shifted 3 up and 3 to the right and 2 to the and 2 up. But then we have this minus in between here, which doesn't fit neither ellipse nor circle, so we should expect to come up with something else besides either one of those two. Let's just graph them and see what we come up with. So we're going to go over there. And our parametric equations are going to look different. Clear this, clear this. They're going to be 2 secant, so 2 divided by cosine plus 3. And they're going to be 4 tangent plus 2. And then we graph and see what happens. Whoa, this looks really kind of interesting. Let me actually zoom out on this one. I'm going to zoom out here relatively close to the center. Actually, the center that you see here, that is actually the described 3 to the right and 2 up. So I'm going to zoom out of this one here, and then I'm going to make the axis look a little bit nicer. I'm going to go to Window, and we don't need a scale of 1 here, maybe a scale of 5, maybe a scale of 5 again. I'm going to go over to y equals, because what it graphs here as well is the asymptotes. Respectively, it connects the points that go out to infinity. So I'm going to see that we're going to graph this a little bit different. dotted line. Let's see if that helps. There we go. Yeah, helps a little bit. Doesn't look very nicely, but what we have is a hyperbola. I'm going to copy this one over here and go back to the lecture. So what we have here is, this is a hyperbola centered at the point +3 +2 as expected, or at least that part was expected, and it opens sideways to left and right. So here's our parabola, and it goes into infinity, and here too. And the lines that you saw earlier, that connects here the last point that it's graphing to the first point of the next part. I don't think I could have done anything about that. Okay, the last example that I have here is the following. Eliminate the parameter t, then graph the original equations. This comes from that, for example, a human cannonball is shot at a speed of 73 miles per, let's see how much that is here, actually 73 feet per second in the horizontal direction, as well as 73.3 feet per second in the vertical direction, which means it's an let's see, oh no, that's not true. It's actually shot at 60 degrees, and that means 73.3 times cosine of 60 degrees. That's the speed in the x direction, and this one here is the speed in the y direction. So this one here comes out to roughly 37 feet per second in the x, and this one comes out to in the neighborhood of 60 feet per second in the y. And then what happens to that human cannonball? Well, it should follow a parabolic arc, upside down parabolic arc, and let's see if that's true by eliminating the parameter t. And this time around we don't have to do something with the Pythagorean because the t is not inside the cosine or the sine. So simply what we're going to do is the second equation we're going to leave like this. And the first equation we're going to solve for t, which is straightforward, x divided by what we find on the right-hand side. And now we substitute. And then when we substitute in here, we're going to come up with a really lengthy expression. So we're going to have this one. And we're going to have this one. And here, when I substitute this one here on the first one, I can actually abbreviate that. Let's see if I need 2 parentheses. Do I have one too many? No, actually I'm fine. This one here, I can abbreviate that because sine over cosine is tangent. And so this one is gone. It's a little shorter. And then 73.73 divided by 73.3 is 1, so this one here is gone as well. And then this one here stays the same. I guess I could write this as a secant squared, but that really doesn't matter a whole lot. I'll be writing this on the side here so I know how to graph this. Y equals x times tangent 60 minus x times 16 over 73.3, oh that's x squared actually, 73.3 times cosine 60 degrees squared. And then as I said, I'll be graphing the original equations. Okay, y equals, so that was parentheses 73.3 times cosine of 60 degrees times t. I might as well check if I'm in degrees. I'm not, so I better be. There we go. And the other one is going to be parentheses 73.3 times sine of 60. Goes into the parentheses times time minus 16 times t squared. Minus 16 actually comes from gravity that whatever you shoot in the air is being pulled down by negative 32 feet per second squared. There's actually a factor of 1/2 in front of that, and that gives negative 16. Okay, our window, how should it look like? It's probably not going to be in the air for 6 seconds, so maybe just 2 seconds or so, I'm just guessing. Step off, I don't know, 0.1 seconds maybe. Let's see, x minimum, well, we're starting at x0. I don't know how far it's going to be shot, so I'm just going to go to 500 feet maybe. Maybe that's too much. It's going to be shot from 0. And how high? Well, probably pretty high as well, so make it maybe 200 feet or so. And then I'm going to go over to y equals, and it's going to graph it nicely. Okay, let's see what happens. Graph, and oh, I guess 2 seconds was enough. And I can actually squeeze the graph in a little bit. So I'm going to make this here to 5 seconds. And the scale here, I may want to do, oh, maybe 50 feet. And the maximum here, oh, maybe 80 feet or so. And then we go at increments of 10 feet for the y, and let's see what happens. And there we go. I don't, actually, it only goes to, what is that, 150 feet, I guess. So maybe go out to 200. And there are the parametric equations for an upside-down parabola. Apparently it goes for a little less than 5 feet or so. I could actually trace it if I wanted to. Actually, we can kind of see it on the side here, that after close to 4 seconds in the table here, that's when it hits the ground at a distance of almost 150 feet. There better be a net there. Okay, and with that, I'm concluding the lecture on parametric equations, and then I'm going to do some problems in the problem section, of course. And I'm just going to insert this last diagram here. So, upside down parabola. I'm done.